Hi guys, today we're going to go over a new section in Chapter 5 that deals with friction. We're going to spend most of the week on this. I again am posting a notes packet with some incorporated examples. Your homework will be out of the book for this stuff on friction, but to limit how many notes you have to take and whatnot, I again put this on here. So I'm not going to read each one of these word for word, but in some of the examples we go over, we're going to use a lot of these terms, and here's all the definitions for you to look back on in the notes. If you forget what any of this stuff means, also some new formulas are down here that we're going to get to on the bottom of the first page. All right, but mostly right now, for the next 10 to 15 minutes, we're going to discuss just the idea of friction, what key factors make friction larger or smaller, and things like that. So let's first take a few simulations to look at here of thinking of friction on its main level of its microscopic level of why it's created. Okay, so this little simulation I'm going to show you guys has us imagine if you could see deep into the molecular level of the makeup of any hard object. Okay, when we take something like most tabletops, they feel very smooth to us to the touch, or maybe even like your textbook. Like in this situation, it shows two textbooks over one another, and usually the covers of a textbook are very, very smooth to the feel. But on a microscopic level, even most things that even feel smooth are bumpy and have a lot of bumps on them. And really the creation of friction comes when these little bumps between surfaces. So I have a chemistry book on top of a physics book in this simulation. Right now, up in the main screen above here, the main view above, you could see that they're not touching. The chemistry book is the blue looking molecules, and the physics books are the green. All right, so right now I have it raised a little bit above, so they're not touching. So of course, if you just move the chemistry book, but it really wasn't in contact yet with the physics book, there's no friction. So number one thing with friction, there's got to be contact. And then when there is, these molecules start rubbing over one another. Right? These make up the structure of whatever these surfaces are made of. They're bumpy on a microscopic level. And they also, you can see a thermometer on here. Most of us probably know this already. Friction does create heat energy. We'll talk about that more when we get to our energy chapter. That's not too concerning to us for the moment, just studying the pure force of it. So one of the key factors this shows me that makes up the entire frictional force, one of the key factors is the roughness or smoothness between the two surfaces, or let's say the texture between the two surfaces. That's one of two main factors that make up the overall force of friction, because the more bumps there are, the more chances these bumps could lock up with one another when trying to slide over one another, right? Seems to hopefully make sense. Now the next factor is how much these two surfaces are pressed together. And that would be the normal force, the force we're already familiar with. The normal force, in most cases right now, but this isn't 100% all the time, in most cases right now, we've learned that the normal force often is equal to the weight of the object. And while that is true on many occasions, it's not 100% true, especially when we get into inclines later this week or next week. So we in general say the normal force and the texture between the objects make up the force of friction. All right, but we have a special name for the texture that represents the texture or the roughness or smoothness between these two objects. We call it the coefficient of friction, and it has its own little special symbol. So now let's go to just looking at some of these definitions, and there's different types and styles of friction we'll get to as well. but going on with what we just discussed a moment ago. All right, we're already familiar with the normal force. It's a force from a surface pushing back on something else. All right, so that we should be familiar with. So this new idea, this roughness or smoothness between the objects in contact, is called the coefficient of friction. And its symbol, this looks like maybe like a cursive U, but it's actually the lowercase Greek letter mu. All right, mu, we would pronounce it mu. Okay, and that's what that represents. Anytime we see this in a formula, it's going to represent a value that the higher it is, the more roughness between the two surfaces, or you could think like more bumpiness between the two surfaces on a microscopic level, right? And if it's closer to 0 and smaller, then those are really smooth surfaces, the textures of them. Typically, this is not always 100% of the case, but most of the time, this value for mu, this coefficient of friction, is between 0 and 1. All right? It's not that it can't be over 1. It's just that in most scenarios, it's rarely over 1. So we say it's typically ranges between 0 and 1. And 0 is really only theoretically. If two surfaces are truly in contact, then there's got to be a little bit of coefficient of friction that's non-zero. So that's why we say between 0 and 1 most of the time. We couldn't have a negative coefficient of friction. That wouldn't make sense. If two things are in contact, there's going to be some at least slight value over 0. All right, so closer to 0 would be two very smooth surfaces. Closer to 1 would be very rough. And remember, this is part of what makes up the overall force of friction. That, along with the normal force, the interaction of the bottom force pushing back the object on the bottom, whatever surface that is, pushing back on whatever object is rubbing on top of it. We've, again, learned that force in the past. All right, now for the different types of friction, and we'll get back to discussing that stuff. So I'm going to use a different simulation for this. This simulation you're going to use for a lab you're going to do later this week that deals with some of this stuff. All right, so we're going to take an object in this simulation. We could see it's just a box on a surface, right? And like we would expect, free body diagram from the past we should already be familiar with. If it's just laying on a flat surface and nothing's even trying to move it, the free body diagram shows weight pointing down, or otherwise known as a force due to gravity, F sub g, and normal force pointing up. And those forces are balanced in a scenario like that, like we always had in the past. If nothing crazy is going on, if this object weighed, I don't know, let's see what it does weigh here, actually, since it says it's a 100-kilogram object. So we should know if we want its weight. We could take its mass, because that's in kilograms, right? That would be its mass down here. If we would take 100 times 9.8, that would give us the weight of this object. So that means this box, this small crate, has a weight of 980 newtons. So if its weight is that pushing into the ground, normal force has to be pushing back with that same amount so it doesn't fall through the floor. So that's all old stuff. Notice something, though. This is a correct free body diagram, and there's no vector arrow for friction. That is because on a flat surface, this is important to remember, on a flat surface, if something is not sliding or trying to slide, then there is no friction, right? Because again, if we think of this, the two books on top of each other simulation here, if two surfaces are laying on top of each other, but not trying to slide across from each other, right? It's not sliding or trying to slide, then these things aren't interlocking horizontally. And therefore, there's no friction. So if the two surfaces are not sliding or trying to slide, there is no friction vector drawn on a free body diagram. But now we have a guy walking up to this thing right here, and he's going to apply a force to it. I have a little force slider here. And notice, I'm going to put a small force, all right? I'm going to put a small force and hold it of about 30, let's go a little higher. You could see some small vector arrows now for our free body diagram. Yet this thing has not moved yet. But let's first look at the applied force. So I have it at about a little over 85 newtons to the right this guy is pushing. But the box is not moving. But the key thing is it's trying to move now. And there now is a force of friction that opposes my applied force. Friction is an opposing force. It always tries to counteract sliding or trying to slide. Right? It always acts opposite the direction of that trying to occur. And it will balance out as long as it hasn't started to move yet. Notice the sizes. Even if I push a little harder, it still hasn't moved yet, right? Now I'm about 100, almost 194 newtons. But the box hasn't moved. But if you notice those vectors on the horizontal axis, the applied force and frictional force vectors, they grew, but still balanced. They're the same size. And that makes sense because remember, back to Newton's first law, we learned about in the past, that we don't have any acceleration on the horizontal axis. So if there are forces, those forces have to be balanced, right? So they're their exact same size. Now we'll discuss the exact type of friction that's going on here. It's called static friction. All right? That's one of our vocab terms, new terms for friction. Static friction is also known as non-sliding friction. So if something is trying to slide because there's at least one force making it try to slide, in this case it's my applied force, but it has not slid yet, that is static friction. But if I slowly keep pushing harder, more than likely, eventually, this thing will start to slide. So far, I'm over 300 newtons. It hasn't slid yet, but it is trying to slide. We see my forces are still balanced, my applied force with my frictional force, because there's no acceleration. But there eventually is some breaking point. And now that it's sliding, we call that kinetic friction. So there's some of our other terms. And they're above on this thing. Static friction, like I just said, is just friction that is present when an object is not sliding, but trying to slide. All right? It has to be trying to slide. So if it's not sliding and friction is present, that means it's obviously trying to slide, then we call it static friction. Once it starts to slide, we call it kinetic friction. We want to be really careful with being specific how we define these, because wheels that are rolling, unless they're locked up and skidding, they're not sliding. So like wheels on your vehicle as you go down the road, as long as you're not skidding or spinning, they're actually undergoing static friction. They might be moving, but any moment the contact of the rubber of your tires on the asphalt on the road are under static conditions. Unless you maybe lock up and start to skid or something like that, and then there's the rubbing that makes it kinetic. We're going to talk about anti-lock brakes in a few moments here to define that scenario a little bit better, something we might be familiar with driving. Okay, but anyways, what's important right now up to this point is really just knowing this terminology. All right, and we'll get to the math in a moment. So number one thing, that both types of friction, now that we know of two types, are dependent on the normal force at the contact point in between the two objects and the texture or smoothness between them. One little example I do, and you could do at home right now, to prove that these two things are the two things that matter, is to just clear out a space on a table or desk in front of you wherever you're working right now. And just put your hand flat on that desk. And just with the normal weight of your hand, don't press down any extra right now, just your dead weight of your hand, just gently slide it towards you. All right, if you're on a smooth tabletop, your hand moves very easily towards you, right? And there is a normal force of the table pushing back on your hand. So the frictional force, once you start to slide, and that would be kinetic friction once you slide, is formed by the product of whatever specific mu value between your hand and the table and the normal force between your hand and your table. And the normal force would be the weight of your hand, since everything's on a horizontal axis, because normal force in many cases is equal to the weight of the object, as we learned. But now I want you to do it a second time. This time, push down as hard as you can and pull your hand towards you. Obviously, it's much more difficult. Why? Because there's more friction. Not because you changed the roughness or smoothness. Your hand's still your hand, and your table's still your tabletop. So the coefficient of friction value, whatever it may be, mu, between your hand and the table, the roughness or smoothness, that's still the same, whether I pushed down harder or didn't, right? Because you kept the surfaces constant. But what you changed was, as far as your desk is concerned, by you pushing down, your hand felt heavier. The two surfaces were in contact with more pressure, right? And this is one reason why we can't say weight all the time, because your hand still weighs whatever your hand weighs, but because you use your muscles to force your hand down in the table more, your table needs to provide a higher normal force back. In other words, your table thinks your hand weighs more, and it has to provide a higher normal force to balance it so your hand doesn't go through it. But that causes a stronger push between the molecules on that microscopic level, right? All the little bumps that could lock together due to the texture of the coefficient of friction. Okay, so that's a good, simple, quick example to understand that. And again, if you're trying to slide but not sliding yet, you're under static friction, and if you're sliding, you're under kinetic friction. So now's the time to look at the formulas involved with this stuff. And they all look kind of the same, but there's some little small differences we have to be careful with, especially with static friction. All right? There's actually two formulas here in our notes with static friction. For the types of problems we're going to do in this chapter, really the only one that's truly going to matter to us when we solve problems is the one with the equality. But I'd only be telling you part of the story if I didn't also view this formula with an inequality and a less than symbol in there. And I'll look to why here in a second. It's because of, under static conditions, there's a breaking point. All right, that will break if you push hard enough. It'll break into motion. There's some exact moment that'll happen. All right, so if you look at a little note beside this formula with the equation, the equality, static friction only ever equals the coefficient of static friction times the normal force when an object is just about to move and break into kinetic friction, the breaking point. This would be when static friction is at its max. Therefore, it's equal to this product of mu times the normal force. And I'll show this in the simulation as well in a second. As you're pushing harder and harder on a steel object, on a non-sliding object, let's say, but not hard enough to slide it yet, your static frictional force builds up to this breaking point value. So at that point, if it's not just about the slide, we have to say it's not equal to mu times normal force. It's some value less than it. And we could show that idea well visually. I'm going to reset all this. We could show that all visually by this guy slowly pushing. I'm going to slowly raise the applied force. Remember, no applied force at all on a flat surface. This box is not trying to slide, so there's not any friction whatsoever yet. And now I put on that little tiny force. All right, and now you can see those vectors forming. I slowly raise it. Notice as I push harder, the frictional force keeps growing with my applied force. In other words, they're balanced. Okay? And this is the main reason why until we get to the breaking point, we have to view the static friction formula as the inequality with a less than symbol, because any moment it's less than its maximum value, because it could grow and grow and grow until that value. Now I hit the breaking point real soon here. Real soon, and Let's get there, let's get there, let's get there. Right about there, I hit a breaking point, and you saw it moved into motion, right? So the breaking point comes, I'm not going to get it perfect on the simulation, but I'm going to get it close. It was somewhere in the 400s, it looks like. So, oops, let me start over. I hit her, let my button go. It's hard to get it perfect, but I'll try. Try to watch this value. When does it break? Maybe it's closer to, right around 500 newtons of applied force. Right around 500. Let me see if I could plug it in manually here. All right, 504, it's already moving. So let's put in 502. Well, reset. Plug in 500 exactly, see if that moves. I want to find that exact value before it actually moves. So 500, we're still good. All right, 501, still good. 502, still good. 503, we're getting close. 504, oh, it's actually even a little bit higher. Somewhere in the little bit of over 500 is what broke this into motion when it was from non-sliding to sliding. And that maximum value, let's just call it 504, all right? It's close to that. That's the breaking point. So back to our notes. If we know that we were told in a problem that an object is just about to move, then we could use this formula as inequality. Mu static times normal force should be 504 for that situation, okay, in this simulation, okay? But as I pushed at any value under 504, it was still static friction, but it built up to that value. So again, if I took mu s times normal force and got 504 newtons, that would mean if I pushed less than that, static will only be what it needs to be to balance you out, how those vectors balanced up till I got the breaking point. That's why there's an inequality version of this formula, all right? But it turns out in this chapter, we're going to deal, when we have static friction problems, we're only going to be dealing with just about to move. Okay, but you still should know that concept. And then, once it did break into motion, start to slide, it was kinetic friction. And kinetic friction doesn't have that concept involved with getting to a breaking point. Okay, so therefore, kinetic friction is always an equality. Now let's notice another thing. The mu values, the coefficient of frictions, if it's in the static frictional formula, the mu has a s as a subscript as well, meaning static, and the k meaning kinetic. That's because the textured values for mu that are between 0 and 1 do differ between the types and styles of friction. So, for example, if you have your textbooks around, if you go to page 129, and this is a very important, I'm going to write a few things down here. This is a very important concept here as well. I'm just going to jot a few things down here if you don't have your book directly in front of you. But on the top of page 129, there's a typical coefficients of friction page. It basically includes typical surfaces that we might do problems with that are in contact with one another. All right, and these are kind of, you could think of more like average values as well, because wood on wood, obviously there's all different styles of wood and textures of wood and sanded or unsanded. So this is just to give you a general idea of these kind of values, this table. But I'm going to use wood on wood as my example. So on page 129 in the table, it says wood on wood are our two surfaces in contact, and its mu static value is equal to 0.5, and its mu kinetic is equal to 0.2. So if we need to look up mu values, remember this table. This table is on page 129. It will be helpful in some of your homework problems throughout this chapter. If they don't give you the mu value and don't ask you to solve for it, but are very specific with what kind of surfaces are in contact, that usually means go to your table on page 129 and look these values up. And you're going to notice something. The mu static values for any two surfaces, like wood on wood here, is always greater than mu kinetic. That's just really a fact of nature. But let me explain it a little deeper why that's the case. Because if you look at every other surface against surface value in this table, you'll notice that the mu-s for that consistent surface to surface is always greater than the mu-k. And if that's true, that means static friction for those surfaces overall would be greater than kinetic friction for those surfaces. Imagine this. We've all probably done something like this before and noticed it, just maybe didn't think about it. Let's say we're in our living rooms or somewhere in our house, especially on maybe like a carpeted floor, especially because carpeted floor, not smooth at all, very rough, right? And let's say you have to move a heavy piece of furniture like a couch. This is going to be my really poor picture of a couch. And you've probably noticed if you ever had to slide a piece of heavy furniture, especially on carpeting, that it seems like it takes a really big force, really big applied force to get it into motion. Especially if it's a real big heavy piece of furniture, couch, desk, something that's pretty heavy. You notice this on. If it's pretty light, you might not ever notice it. But once it starts to actually get into motion, then it seems like you don't have to push quite as hard. Your force could be smaller. And there's truth to that in friction. Keeping something sliding as opposed to getting it sliding in the first place, especially when there's significant friction and a really heavy object involved. It takes less force to keep something moving than to get it moving in the first place. But that sounds a lot like Newton's first law anyway. Because objects at rest want to stay at rest, and objects in motion want to stay in motion. And to go from rest to motion, you need to cause acceleration. And you need to break that static friction, which is always greater because the mu value is always greater, and get it into a kinetic sliding friction where the mu value is lower. And if there's less friction once it's sliding, you don't have to push as hard anymore over here to keep it moving. All right, so I hope maybe some of us noticed that before. But that is mainly because of these mu values. The static version and the kinetic version, as long as the two surfaces are in contact are consistent, will always come out mu static bigger than mu kinetic. You could see in the table on page 129 other values that all these values have that same trend. All right, so because of that fact, I want to go over another thing that we may be a little familiar with, at least using, maybe not everything about it, and that's anti-lock brake systems. Because scientists and engineers have known for many, many, many years this idea of friction and what makes it up and these mu values. Okay? But sometimes it takes many years to develop the right technology to take advantage of some of these ideas that were known for a long time. And that occurred with braking systems and how they developed over time in vehicles. So I know not everybody out there has a real good idea of braking systems. So I'll first go to a picture and to describe what I'm going to talk about here. This is a picture of what's called a rotor. This is mounted on the wheel of your car. All right. This is a brake pad. All right. Brake pads could have slightly different designs, but all brake pads look like almost like a slight arc that's attached to the rotor. Some of you may be washing your car or noticing it on some cars that have pretty open rims, sometimes you notice a very shiny or possibly rusty disc behind the rim of a wheel. That's what this is. It's the rotor. And it's what your brake pad clamps to stop your vehicle. And pretty much all modern vehicles nowadays have anti-lock braking systems that take advantage of this idea of friction being higher under static conditions as opposed to being lower under sliding kinetic conditions. All right. In the older days of cars, not all that long ago, but you're probably most of your parents would probably know this. When learning to drive a vehicle, you would be told, if your vehicle was not anti-lock brake, did not have anti-lock brakes, that it's a good idea to pump the brake manually with your foot so you don't slide when you brake. And the reasoning behind that was the idea of the different styles of friction. Okay, so when you hit the brake, this brake pad clamps on to this rotor, which is attached to your wheel. And just imagine your vehicle, big vehicle that has a lot of inertia, right? A lot of inertia, has a lot of mass. Even a small vehicle, all things considered, has a pretty good bit of mass. It's going to take a pretty big force to stop it. But in the days of non-anti-lock braking systems, when you hit your brake pedal, this brake pedal or this brake pad locks up to this rotor, and your car has a good chance of sliding if you just hold in the brake, especially if you're going at any decent speed, because it literally does that. It locks up your brake, and the grip on your tire, just between your tires and the road, just isn't strong enough to not slide. And you break into a sliding fashion, and once you start to slide, you are now in a kinetic conditions. And on page 129 of your book, let's just not even think about wet roads right now. But in this table on page 129, you could see rubber on dry concrete. Under static conditions, the mu value, flip back to here, for rubber on dry concrete is 0.8. Under kinetic conditions, it drops to 0.65. Now you might say, oh, that's not a big drop, but it really is, because these numbers are between 0 and 1. So that's actually a 15, or typically between 0 and 1. So that's a 15% drop, therefore, in the amount of friction you have stopping your vehicle if you start to slide. You want to be under non-sliding conditions. So, again, this was known. This science behind this has been known for a long time, and that's why people were told before anti-lock braking systems to pump the brake. And that tries to gradually stop you while keeping you under static conditions, where the mu value that is part of what makes up your overall force of static friction, stays static and doesn't go to kinetic friction by sliding. And not only will it stop you faster, since it's going to be a higher mu value involved, you'll also have a better chance to control your vehicle, because we probably all know, if you ever slid on ice, that you could go anywhere. But if you were even sliding on concrete because you locked up your wheels, you could still just go anywhere. You could get flung anywhere out of control. So it not only helps you have a higher force of friction, it helps you control better because you're not sliding. All things that make things more safe, right? But here was the problem. Most of the time when you slam on your brakes, it's probably because, and don't just gently brake, it's probably because something surprised you. You might be just about to be in an accident, something like that, right? And it's easy to tell somebody you should pump your brakes in a situation like that. But most people's natural reaction in a scenario where there might be an accident is to slam on their brakes and just hold it there. And that causes many accidents that maybe you could avoid if you could have stayed in static friction as opposed to trying to avoid kinetic friction. So eventually, engineers came up with the anti-lock braking system to help you, so it takes the thought out of the process. And now when you hold in your brake, you could even feel it, especially if you gently push in your brake, guys. We've all probably experienced this. You feel a little pump action pumping back. That's your anti-lock braking system that's taking this brake pad on your rotor and in intervals locking it up. Or I don't want to say locking up. In intervals grabbing onto your rotor. So it avoids locking up. Is it perfect? No. If you're going at very great speeds and still slam on anti-lock brakes, especially in non-dry conditions, but it could happen even in dry conditions. If you're going extraordinarily fast and slam on anti-lock brakes, they'll still do their anti-lock process, but in the moments of them gripping, they could lock up little bits at a time. It's not perfect, but it does avoid it pretty well. All right, it does avoid it pretty well. And it helps you stay under static conditions as opposed to kinetic. And just to reiterate what I said, this is a very short video we're going to just all watch together right now of this being explained with a little simulation as well.
When the driver fully applies the brakes in a vehicle without the anti-lock brake system, the brakes can lock. This causes the wheels to stop turning, which makes the tires skid. Skidding tires have very little grip and are not effective at stopping or turning the vehicle, so the driver may be unable to take evasive action. With ABS, when the driver fully applies the brakes, the system uses sensors to detect any brake lockup and rapidly pulses that brake to prevent it from locking. This helps to prevent skidding so the tires can maintain grip. It also helps to allow the vehicle to be steered around obstacles while braking. One way to think of ABS is allows braking and steering.
Oh, I'm sorry, I think my video recording paused, so I'm just going to back up to discussing what I was going over at the end of the video. So again, hopefully this anti-lock brake ID, as well as like trying to get a couch pushed in your living room or something like that, hopefully you can make some connections here with some real aspects of static as opposed to kinetic friction. The most important thing before doing problems is understanding the concepts. And since this took a little longer than I planned to discuss this stuff, I'm going to count this lesson for both Monday and Tuesday this week. So we are going to continue in a moment here with a few example problems. Okay, but this lesson and discussion right now, as well as these few problems I'm getting into right now, and the homework, will be your work for both Monday and Tuesday. We won't move on until Wednesday. Okay, until another type of problem, friction problem. All right, so at this point I'm going to go over to our notes again. And I broke it up into some general scenarios that we could put a lot of this stuff in. Now, the two general categories of friction problems that we're doing in this chapter are going to be considered balanced and unbalanced. And there's a couple different balance scenarios we're going to do today. Unbalanced will wait till later in the week, maybe Wednesday. Just to not throw too much at you guys at once. All right, so the first scenario, and we're going to think and still use some examples maybe that we discussed earlier. Balance friction scenario 1, sliding an object at constant speed. And by the way, I will again post these finished notes. So there'll be a blank copy if you want to do these with me. You could print that off and fill it in, but I'll also include the completed notes when I post this lesson. Alright, so for scenario 1, the first thing we do, I have FBD here. We're going to draw a general free body diagram for an object sliding at a constant speed. So we are sliding, so that is kinetic friction we will be dealing with. And it also says constant speed. Alright, so two important things here. The fact that it says sliding means we're going to be under kinetic friction, not static. FFK, yes, that is a K. It's hard to write small on this thing sometimes. And constant speed means acceleration is 0. We should know that from the past. Excuse me. So let's draw a free body diagram of an object undergoing something like this. To slide at a constant speed, we have to continually apply an applied force to counteract the force of friction in the opposite direction. But if we slide at a constant speed, that means these two forces are balanced with one another. It all goes back to Newton's first law again, which part of it said things moving at constant speed will continue moving at constant speed unless an unbalanced force is applied. All right? So that means if we are at constant speed, the forces must be balanced. Whatever I'm pushing at with my applied force equals kinetic frictional force, and we'll prove that in a mathematical statement. And we do have forces on the y-axis as well. Weight pointing down, or force due to gravity, and normal up. And in a scenario like this, where there's a flat surface, and where we're pushing horizontally on a flat surface, normal force does equal the weight. We learned that before. Now that's not always the case, especially when we get into like hills and inclines. But on a flat surface, when we're applying a force horizontally, normal force equals the weight, and we can see that they're balanced. That's why it doesn't fall through the surface we're on. So that's the correct free body diagram. And now we're going to apply the mathematical equation of Newton's second law on the x-axis. Because what we're usually going to want to solve for here are things about applied forces, frictional forces, or anything that's involved with frictional forces. So, it's the setup equation. We all know from the past, we've used this a million times now before, F net, specifically on the horizontal axis, equals ma. I already said, though, that a is 0, right? But let's break down F net. F net, like always, is the total of forces on the axis we're focused on, right? The x-axis is the one we're focused on here. Let's make right positive, left negative. So it would be the applied force minus the frictional kinetic force. Or essentially, these two forces are basically like playing tug-of-war on one another, right? We did tug-of-war problems. So we set it up similar to that. Applied force minus kinetic friction equals mass, but acceleration, since we're at constant speed, is 0. And that leads me to a simple conclusion. And it's written down here, so I'm not going to rewrite it. If that all equals 0, because any mass times 0 is 0, I could add that friction to the other side, the kinetic friction, and we could see in this kind of scenario, the applied force equals the kinetic frictional force. That's why we call this a balanced friction scenario, because my kinetic friction is in balance, is the same size, magnitude as the applied force. That's where this gets its name, balanced scenario. Okay? So that's the concept involved. That's the generic free body diagram for anything sliding at a constant speed. The applied force balances with the kinetic frictional force on a flat surface push like this. Okay? So now let's get into an example with specific numbers. I'm not going to redraw a free body diagram. I'll just keep referring to this one since it's the same kind of scenario. Let's just put in numbers. I will do the math from scratch, though, just to explain it one more time. It says you push a 25 kilogram wooden box across a wood floor at a constant speed of 1 meter per second. Constant speed tells me A equals 0. And this is important. It does tell me what the constant speed is, but this really doesn't matter. What matters is we're pushing at a constant speed. Nowhere in my formula for figuring out any of this stuff is the V of constant speed necessary. What's necessary is me to pick out that because it's a constant speed, A is equal to 0. I mean, if you list your V here of 1 meter per second, that's fine, but you're not going to use it anywhere. It doesn't really matter what the constant speed here is. It matters that it's constant, and A is 0. All right, so it wants us to figure out how much force we exert on the box. That would be our applied force, how much we exert, right? How much you exert on this. That's the unknown. And here's what I mentioned earlier. You might remember. If we're not asked for a solve from you, but we need it and weren't given it, but we were given the specific types of surfaces in contact, that usually means you need to look it up in a table. And don't forget, that table is on page 129 of your textbooks. Okay? So you may need to flip to that in the condition that you need mu and you know the specific surfaces. If we're asked to solve from you find it mathematically. All right, so we know we're in sliding kinetic conditions. So when I look up wood on wood, I may need to make sure I use the mu kinetic, not the mu static. And the mu k for wood on wood is 0.2. All right, so there's all our givens. And how we set this up is like I set up the formula above, but I'm going to reset it up. We all start with Newton's second law, and the applied force is on the x-axis, so we want to set up Newton's second law on the x horizontal axis. All right, F net on the x-axis is ma. The free body diagram above still applies here. I'm pushing one way or pushing or pulling with an applied force one way, and kinetic friction is opposite. So that means the net force, the total of all forces on the x-axis, is the applied minus FFK, because it's in the opposite direction. And acceleration is 0. So yes, we were given mass, but at this point it doesn't even matter, because anything times 0, and that's because it was moving at constant speed, is 0. And that means this is a balanced scenario because I could add FFK algebraically to the other side, and I just mathematically proved, but I got to break it down more, that those two are balanced and equal. So if I could find my kinetic frictional force, I could find my applied force because they're equal. Okay? So I'm going to continue my work over here. So now at this point, I could say, now follow with me here so you don't get lost. This is simple, but some students get lost here not paying attention well. All right? We have a formula for kinetic friction. It is mu kinetic times the normal force, right? So I am subbing in from that new formula on the front page of your notes. FFK, I'm subbing in this expression, mu k times normal force. So I'm making a substitution there. All right? And therefore, that's still equal to the applied force because of it telling me that up here. Now, I don't know the normal force, but I do know another thing that I mentioned as we were setting up the problem and in the free body diagram in the general scenario above. On a flat surface, when your applied force is horizontal, your normal force equals your weight. And what does our weight equal? This is something you should remember from the past. M times little g, right? So I can make another substitution. Mu k mg. And now I'm going to plug in the values. So mu k was 0.2. And I'm really running out of room here. I apologize. So tell you what, I'm running out of room, so I'll try to do it underneath. So once I plug into this 0.2 multiplied by our mass, which is 25, and little g, as long as we're on Earth, is 9.8. Run those numbers, and my applied force is 49 newtons. My applied force and my kinetic frictional force is equal to that much. Get that out of there again. Let me go full screen here so you can see all that. And this was called balance because both of them are at that. Now let's take this to a concept a little further. All right. What if I started pushing harder now? All right. Kinetic friction is that value. It's 49. It won't change, and here's why. Even if I started pushing harder or even started pushing softer, kinetic friction straight up is U times the normal force. So whether I push harder or softer, mu represents the coefficient of friction, the roughness or smoothness between the objects. So whether I push harder or softer, that won't change what the two materials are made up of, right? And as long as I continue to push horizontally, harder or softer, that won't change the fact that the normal force is equal to the weight. So once I find the kinetic frictional force, assuming the textures and the normal force stayed consistent, that 49 newtons is always going to be the kinetic frictional force on this object when it's sliding. But what I could change is my applied force. In this particular problem, it was balanced, and that's why we solved it this way. But let's say I saw a sudden start pushing at 60 newtons of force on this object. If I start pushing harder than friction is pulling against me, remember I said this is like tug of war, you're playing with applied force and friction. If I push harder than 49 newtons, this thing will start to speed up. Remember, these are the exact, 49 newtons is the exact perfect value to push out to keep it going constant based on the specific mass and mu value given in this problem. But if I push harder than 49 newtons and kinetic friction is still 49 newtons, this thing would speed up. It wouldn't be constant anymore. Then we'd be in an unbalanced scenario, which we'll get into later in the week. Another thing that could happen, when you're pushing something, especially something heavy and maybe for a long time, sliding it, you might get tired. And maybe you can no longer push with 49 newtons if you get tired, right? Maybe you now can only push 30 newtons. If that's the case, kinetic friction while you're in motion and sliding is still going to be 49 newtons. But if you can't push with 49 newtons anymore, then kinetic friction is going to start winning the tug of war in the opposite direction. It'll start to slow you down, and you won't be at constant anymore, and you'll be unbalanced. So scenarios can change, but this scenario, because I was constant, we solved it in such a fashion where A was 0, where those two forces were balanced, and both were 49. All right, again, I will post this fully done example for you to look at your convenience. One more balanced scenario. Let's go to scenario 2. That last scenario was a balanced friction problem with kinetic friction. This is going to be with static. And the first thing we're told in this one is an object is just about to move. Just about to move basically means, as we were describing before using the simulation, the lab simulation that you'll use later in the week, that there's some breaking point. You push, you push, you push. Little by little, your applied force builds up, and eventually, if you push hard enough, you'll get an object to start sliding into motion. So if a problem tells us that it's just starting or just about to move or just starts to move, any kind of wording like that, we assume we're just right at the breaking point, but we really haven't moved yet. Even if it says just starts to move or begins to move, that means it's tipping off to we're at the breaking point where we're at our max static. And that's when we could use, when needed, FF static equals mu static times the normal force. We could use the equality. Don't have to worry about the less than symbol if we're at the breaking point, all right, and use it as a straight up equality. And if we're just beginning to move, or just starting, but really haven't yet, it also means that your acceleration is 0 still, which is what's going to lead us to this still being a balanced friction problem. So our free body diagram for this looks a lot like the last one. We have an applied force in one direction, but at the breaking point, it will equal and balance with your static friction. It's static because we have not quite yet begun to slide. We're just going to, though. We're like at that threshold. And we still have weight and normal force actually balancing out with each other on the y-axis. So we would again go to Newton's second law. F net on the x-axis equals ma. And the horizontal forces, totaling them up, their net, in other words, is applied force minus the static frictional force. And that's m times 0. So we get a very similar result to the last problem. If this all equals 0, then we could flip FF static like we do right here to the other side. And this is again why we call this a balanced scenario. Because applied force in this kind of scenario where something is just about to move or just starts to begin motion, any kind of wording like that means that applied force equals static frictional force. So now let's go and do this on an example problem, right? So we'll have the mass given again, a 50 kilogram table in this case we're going to push. This time we're going to be given the applied force. I know that I'm pushing with 300 newtons, and it just begins to move. So that's important there. Just begins to move. Just starts moving. Any wording like that still means A is 0. Remember, A is 0 when you're not moving or just about to break into motion, and A is 0 when you're at constant motion, right? Constant speed, like in the last problem. This time, we want to find the coefficient of static friction. We're not looking it up in a table. We couldn't. We don't know what this floor is made out of. We don't know what this table is made out of. We can't look this value up in a table without knowing the specific values. And also, remember those tables, even when we do use them, are average values of those types. There could be all kind of variations of materials. So if you really want to get a true mu static value with two specific surfaces, you do it experimentally and use this kind of math to solve for it. All right, so we I'll reset up the problem from above. Net force on the x-axis equals ma. Applied force minus, using the free body diagram from above, ff static this time equals m times 0, which again led us to believe these are balanced. And as long as I'm at my breaking point, like I said above here, that I could use this formula as an equality. Okay? So FA equals FF static. So that actually, if we didn't already realize that, we could list another given here. FF static is also 300. If I know they're balanced, and I know the applied force, I also know the static frictional force. That's what we just proved right here. All right? But our goal is to find the mu, so I got to break it down. I'm going to do that substitution. If applied force equals static friction, and from one of our new core equations for static friction, at the breaking point, it equals mu static times the normal force, right? And one more substitution. Mu static times mg, because remember, normal force equals mass times little g, because in this scenario, the normal force is balancing with the weight on the y-axis, F sub g. So now that we made all those substitutions after proving the balance here, mu static equals, we'll just do a little division here, static friction, which we now know is 300 because it's balanced with applied force, mg, and that's going to be 300 divided by 50 times 9.8. Don't forget what this number is supposed to come out as. It's supposed to come out as a number that's typically between 0 and 1. So if you're solving for this and don't get out something between 0 and 1, I would definitely recheck your work. You likely did something wrong. It's 0.61. And since this is the first time we solve for it, now is where I want to talk about something that might seem strange at first, because we're so used to units. Mu does not have units. It's one of the few unitless values we run into. A conceptual reason why mu doesn't have units is because it's like thinking, remember, it's between 0 and 1. It's like me kind of saying, like on a scale of 0 to 1 approximately, how much roughness or smoothness are there between two surfaces? So it's like a scaled value, where closer to 0 is very smooth, closer to 1 is very rough surfaces together. All right, so this is a little bit over halfway, 0.61 in this problem. Getting to the point of fairly rough, since we're past halfway of what it typically is in between. But purely mathematically, why mu has no unit is because it cancels out as well. So let's just go to the straight up formula with no numbers that we just used right here. US times normal force. And let's just solve this this core formula to isolate mu. We have gives a static friction over normal force, right? Static frictional force over normal force. Forces are in newtons. So if we just straight up knew the static frictional force was like 100 newtons and the normal force was 50 newtons, well, I should actually use a different value. Let's say 200 newtons. You would see we get 0.5 and newtons would cancel out, leaving me a unitless value. So that's the reason mathematically it just fully cancels, it goes away. But I want everybody to realize that mu, the coefficient of friction, is not the force of friction. It's part, like we started this discussion today with, it's part of what makes up the force of friction. It times the normal force is what makes up the force of friction. Okay, so I know this was a lot today. I want you guys, and I'm going to post these with the assignment, but I'll write them here. Based off these two scenarios, I want you guys to try to do page 128, numbers 17 through 20. These are all balanced problems. Read them carefully. They're similar to the examples. Like always, these will just be spot checked. Make sure you upload them in a easy to view photo. Most of us have been doing a great job with that, but some of the homework I've been having some trouble making out. Okay? It's been a little blurry or whatnot. Just make sure you view your own pictures before you post them so I could see them well. And also, I would greatly appreciate it if you guys, when you upload your pictures, that they are vertical and not sideways. Because, yes, I can rotate them, but I have to open them outside of Google Classroom to rotate your pictures if they're not vertical already. So if you could, please take them and post them in a fashion where the work is vertical and not sideways. I'm not going to take off points or anything like that. I'm just asking you guys to please do that because it just takes me a long time to open up many of them in a whole nother window every time I'm going through Google Classroom to check these or spot check them if they're sideways. All right, thanks guys, and we will go over these later in the week. At some point later in this week, probably after we do the next lesson, I will do a live video, maybe Thursday or Friday, it looks like. We'll see. Of us going over these. Okay?